Welcome to AI Paper Slop. Today we're looking at a breakthrough paper from researchers at Huawei Noah's Ark Lab, Huawei Celia team, and 2012 labs titled Faster-WAM. Do world action models need deep action modules? And if you are building robot policies, here is the core insight you need immediately. World action models, or WAMs, have traditionally suffered from massive inference latency because their action modules mirror the exact layer depth of their heavy video backbones.
Which is a huge bottleneck in practice.
Exactly. Well, this paper completely dismantles that design constraint. They introduce a framework called Dock of Transformer, or DUDO-T. They deploy a 30-layer video diffusion transformer as a pure representation hub, and they literally just snap on a lightweight single-layer action head. By solving the mathematical mismatch between video and action positional embeddings and fusing keys and values across all 30 layers, Faster-WAM achieves a 3.2x speedup over Fast-WAM. It hits 66.5 milliseconds per inference and actually boosts out-of-distribution generalization on LIBERO-Plus to 75%.
Yeah, and it completely upends the prevailing assumption in embodied AI right now.
Yeah.
I mean, for a while, the consensus has been that if you want a policy capable of nuanced high-dexterity manipulation, you just have to pay the compute tax for a deep action module.
Right. The conventional wisdom basically said you needed that massive capacity.
Exactly, to project visual features into complex motor spaces. But this paper argues the complete opposite. The physical dynamics, the intuitive physics, the spatial relationships, they are all already fully materialized in the internal representations of the video world model. You don't need a deep action network to relearn those dynamics. You just need a specialized readout head to extract them.
And to really grasp how they pull this off, we have to look at the WAM bottleneck and the mixture of transformers, or MOT trap. Let's map the landscape for you. If you're building state-of-the-art robot policies today, you're probably heavily invested in vision language action models, right? VLAs like Pi0 or Pi0.5.
Right, because VLAs are incredibly attractive. They map visual observations and language instructions directly to action chunks.
Yeah, I mean, a model like Pi0.5 is pulling about 71.4 milliseconds per action chunk. That gets you to a control frequency that's actually viable for reactive, real-time closed-loop control.
But they are still fundamentally direct mappers. They don't explicitly simulate the future state of the world, which is why world action models take the generative approach. They center the action prediction on video generation models, pre-trained on massive-scale internet video.
Because they're predicting future frames, they have to internally model temporal evolution and object permanence, right?
Exactly. They inherently possess a structural understanding of how the physical world behaves. But that structural advantage comes at a severe cost to inference speed. Fast-WAM was essentially the low latency benchmark for this category, and it still takes 211.7 milliseconds per action chunk.
Which is practically unusable for high-frequency control. You're looking at, what, a 5 Hz control loop? Yeah. If a robot is trying to catch a falling object or adjust to a slipping grip, lagging by 1/5 of a second on every single forward pass is just a non-starter.
It's way too slow. And the bottleneck isn't even just the sheer size of the video model. It's the MOT architecture itself.
The mixture of transformers setup.
Yeah. To enable single-pass joint training, where the video and action streams share attention, the architecture enforces this rigid one-to-one layer correspondence. So a 30-layer video DIT absolutely mandates a 30-layer action DIT.
It's honestly like a rigid corporate hierarchy. It's like forcing a lightweight intern being the action model to mirror the exact 30-step complex workflow of a senior engineer, the video model, just so they can communicate.
That's a great way to put it. The video stream is processing these dense spatio-temporal representations, while the action stream handles proprioception and action tokens, but they're locked in this synchronized forward pass.
Layer 1 attends to layer 1, layer 15 to 15, and so on.
Right. You are forcing the action stream to duplicate the computational depth of the video stream purely to maintain the shared attention mask.
But, okay, my immediate thought when reviewing the MOT literature was always, why not just chop off 29 layers of the action model? If the action space is low dimensional, why can't you just run a 30-layer video backbone and a 4-layer action head? What breaks if you do that?
Well, the problem with truncation in the standard MOT framework is the massive loss of hierarchical semantics. If you restrict your action model to, say, only 4 layers, and it only attends to the first 4 layers of the video backbone, you are completely starving the policy of high-level features.
Because the early layers are just seeing basic shapes and colors.
Exactly. The shallow layers of a vision transformer or a DIT are primarily extracting localized edge gradients, textures, high-frequency spatial details. The deeper layers 20 through 30 That's where the model constructs semantic understanding, temporal consistency, complex object relationships.
So a shallow action model in an MOT setup would just never see those crucial representations.
Never. I mean, there were attempts at asymmetric designs like H-bridge, which tried to introduce fixed cross-stream connections at specific intermediate layers. But it still relied on predetermined, ordered interactions. It didn't solve the core issue of allowing a lightweight action head to dynamically sample the entire representational depth of the backbone.
Which sets the stage perfectly for the dock of transformer, or not T paradigm, right? The Huawei team completely abandons that parallel stream OP design. Instead, they shift to a hub-and-spoke architecture.
Right. They treat the video backbone as the centralized frozen representation hub, and they treat the task-specific heads, in this case, the action prediction module, as separate nodes that just connect via explicit docking interfaces.
And the specific instantiation here, Faster-WAM, really highlights the parameter asymmetry this allows. They use WAN 2.2 TI2v5b as the frozen hub, so that's a 30-layer video DIT with roughly 5 billion parameters.
And the action head they dock onto it is literally just one single transformer layer.
Yeah.
It has a hidden dimension of 1024.
Just one layer, that's what, about 30 million parameters, plus another 20 million for the docking interface. So you have a 5 billion parameter physics engine and a 50 million parameter trainable adapter just routing those physics into motor commands.
The parameter ratio is wild. But as you can imagine, it introduces a massive dimensionality problem.
Oh, absolutely. How does a single layer parse representations distributed across 30 layers of a massive video DIT without getting completely overwhelmed by the feature space differences? I mean, if you naively concatenate the keys and values from 30 layers of a 5B model, you'd blow out the memory on any standard GPU immediately.
And the attention mechanism in that single action layer would just choke on the noise. So they navigate that dimensionality trap using the KV fusion mechanism.
Okay, break that down for us.
So the video hub is computing keys and values for the conditioning frame at every single one of its 30 layers. The docking interface has to compress that tensor down into something manageable. They handle this via two explicit transformations, channel mixing and layer mixing.
Channel mixing makes intuitive sense to me. The video hub and the action head are operating in different learned feature spaces, so they need to project the video keys and values using separate learned weight matrices to map them into the 1024-dimensional feature space of the action head.
Exactly. Now they are at least mathematically aligned in terms of feature dimensions. But you still have the L dimension. You still have 30 distinct layers of features to deal with.
Right, so how do they flatten that?
That is where the layer mixing matrix comes in. They apply a learnable cross-layer aggregation matrix over that layer dimension. It essentially computes a weighted combination of the channel mix video keys and values across all 30 layers.
And they use the same learnable aggregation coefficients for both the keys and the values.
Yes, which is crucial. It ensures that the relationship between a key and its corresponding value isn't distorted during compression. The output is this single, unified KV cache representing aggregated temporal and spatial dynamics from the entire depth of the video model.
Compressed down into a single sequence length that the one-layer action head can actually process via mixed context attention. What I found fascinating was figure 3B in the paper, where they visualize exactly where the action head is pulling its signal from.
Oh yeah, the distribution of those learnable layer mixing wakes.
Right. It isn't uniform, and it doesn't just spike at the final layer like you might expect. The strongest signals are heavily concentrated in the intermediate layers of the video backbone.
Which makes a lot of sense when you think about it. The intermediate layers of deep generative models are typically where the most actionable physical representations actually live.
Because the earliest layers are too focused on pixel-level noise, right?
Exactly. And the final layers are often overly abstracted into pure semantic concepts just for language alignment. But the intermediate layers, say layers 10 through 22, that's where the model calculates spatial layouts, object permanence, collision dynamics. That is exactly the latent space a robot policy needs to tap into.
But the weights don't zero out at the edges either. The signal remains distributed across the entire 30-layer depth. The one-layer action head is pulling edge detection from layer 2, object relationships from layer 15, and task semantics from layer 29, all simultaneously.
Yeah, and fusing the features across the entire depth is what makes the one-layer head viable. If they had hard-coded the interface to only pull from layer 15, they would lose the fine-grained spatial precision of the early layers and the task-level context of the deep layers. The network basically learns how to dynamically weight those resolutions based on the task.
But fusing the features only solves half the problem. Fusing the data is great, but we really need to talk about the coordinate system mismatch that plagued older MOT architectures. Let's get into the rotary positional embeddings, or ROPE.
ROPE is standard across most modern transformer architectures, but dealing with it in a cross-modal setting is notoriously difficult. It encodes absolute position by rotating the query and key vectors in a complex plane.
Right, and the key property of ROPE is that the dot product of a rotated query and a rotated key depends exclusively on their relative displacement.
Yes, that relative distance decay is absolutely essential for sequence modeling. But in a world action model, your two modalities have completely different dimensional bases.
The video backbone is processing spatiotemporal patches. It has a temporal axis, a width axis, and a height axis. So the frozen DDT applies 3D rope.
Exactly. It partitions the feature channels and applies distinct rotation matrices for time, height, and width. But the action sequence is a purely one-dimensional time series. Action step 1, step 2, step 3. So the action queries naturally use 1D ROPE.
Okay, so frame this mathematically for the listener. If you take a dot product between a query rotated in 1D and a key rotated in 3D, that relative displacement property of rope is just completely destroyed.
It is. You trigger a severe frequency basis collision. The cross-modal attention logic ends up depending on the absolute action and video coordinates jointly, rather than their relative offset.
It's like trying to calculate a trajectory by overlaying a 1D ruler randomly onto a 3D topographic map. The math just yields garbage offsets because the frequency bases and coordinate systems don't match.
That's a perfect analogy. You just get positional noise. And in traditional shared attention OD architectures, this misalignment was totally unavoidable. Because the forward path was shared, a key could only be rotated once.
So they just had to absorb the degraded signal.
Pretty much. They couldn't maintain separate positional encodings for the video self-attention and the cross-modal attention. But because DuDo-T decouples the hub from the head, Faster-WAM can execute what they call an unrotate, fuse, re-rotate pipeline.
Okay, walk us through that pipeline.
Well, they exploit the mathematical properties of the ROPE rotation matrix. Because the rotation matrix is orthogonal, its transpose is its inverse. So they take the cached video keys from the 30 layers, multiply them by the transpose of the 3D rotation matrix, and unrotate them back to a canonical flat feature space.
They mathematically strip the 3D positional encoding right out of the keys.
Exactly. Then, once the vectors are in that unrotated space, they run the KV fusion. After that, they normalize, and finally apply 1D ROPE to those fused video tokens.
So now the fused video keys and the action queries are operating on the exact same one-dimensional positional basis.
Right before the mixed context attention operation, yes.
They flatten the 3D topographic map, fuse the data, and then re-rotate it to match the 1D ruler of the action head. It's such elegant matrix manipulation. And looking at their ablation studies, implementing this ROPE realignment alone jumped the model's LIBERO-Plus generalization success rate from 66.8% to 71.3%. Just fixing the coordinate math gave them a massive 4.5% bump.
It really reveals how much representational capacity was being wasted in older architectures, just trying to learn around that positional noise. When the attention mechanism preserves relative distance, the action head can precisely localize visual features, which is critical for dynamic manipulation tasks.
Okay, so now that the architecture is optimized mathematically, we should talk about how they ruthlessly optimized it functionally. Because they made a very bold design choice. They completely stripped text cross-attention out of the action head.
Yeah, in a standard setup, you'd inject the text instruction like place the apple in the bowl into both the vision backbone and the action module to ground the language.
But the Faster-WAM authors realized the 30-layer video hub already heavily processes the language instructions, right?
Exactly. The 30-layer DDIT is already parsing the language and using it to isolate the relevant semantic and physical features in the video latent space. So routing text embeddings into the one-layer action head is redundant.
It's probably detrimental. You'd be forcing a tiny 30 million parameter layer to dedicate its limited capacity to complex language grounding.
Which it's poorly equipped to handle compared to the 5 billion parameter hub. So by entirely removing text cross-attention, they force all instruction conditioning to bottleneck purely through the video hub's physical representations. The action head doesn't need to understand language. It only needs to decode the physics representations that the hub has already filtered.
And that pushes the LIBERO-Plus score to its final 75.0%. Okay, let's hit the benchmark speed run, because latency is the whole point of this paper. Fast-WAM was sitting at 211.7 milliseconds. The Pi0 VLA is at 68.2 milliseconds.
And Faster-WAM clocks in at 66.5 milliseconds per 32-step action chunk.
That destroys Fast-WAM and even edges out state-of-the-art VLAs like Pi0. 66.5 milliseconds gets you to roughly a 15 Hz control frequency.
Which is well within the envelope for reactive closed-loop manipulation. And they achieved that speed up while maintaining state-of-the-art performance on standard tasks. 98.50% on standard LIBERO and 89.17% on RoboTwin 2.0.
Which tests complex bimanual manipulation in randomized scenes. And they didn't even need massive scale embodied pre-training to hit those numbers, did they?
Nope. The action head was trained from scratch, strictly on the target datasets. But the out-of-distribution generalization is the real kicker here.
Oh, yeah. LIBERO-Plus is designed to test policy robustness against massive distribution shifts, new backgrounds, lighting, camera shifts, sensor noise. Fast-WAM, with its full 30-layer action module, scored 51.5% overall. Faster-WAM scored 75.0%. That is a massive 23.5 percentage point leap.
And if you look at the perturbation categories, robustness to camera shifts went from 16.4% in Fast-WAM to 67.9% in Faster-WAM. Sensor noise robustness jumped from 37.7% to 82.3%.
There is such a profound irony there for the listener. By stripping away 29 layers of the action model, making it fundamentally smaller and less capable, the resulting robot policy actually became wildly more robust to sensor noise and visual shifts.
It's textbook addition by subtraction. A 30-layer action model has the capacity to overfit to specific lighting and noise in the training data. A one-layer action model simply lacks the parameter count to memorize that noise.
It's forced to rely entirely on the generalizable, robust physics engine of the frozen video hub.
Exactly. The Video Hub, having been trained on billions of diverse internet frames, understands the underlying physical reality regardless of the noise or the camera angle. The single-layer action head trusts that representation because it doesn't have the capacity to compute an alternative.
This fundamentally shifts the paradigm of embodied AI. We are moving away from co-training dual deep networks for vision and action.
Right. We're moving toward a model where you scale a world model to massive proportions, freeze it, and just use a lightweight decoder to puppeteer the hardware based on the world model's internal state.
Which leaves me with a final, somewhat provocative thought for you to ponder as you update your own architectures. If a single transformer layer, just 30 million parameters, is all it takes to decode complex robotic actions from a video model's internal representations, are we currently over-engineering the action part of vision language action models?
It's a great question. It suggests the bottleneck in robotics isn't control capacity, it's physical reasoning.
Exactly. Perhaps the future of robotics isn't about training better, deeper control policies at all. Maybe the control problem is actually trivial once the model possesses a sufficient understanding of physics. Perhaps the future scaling laws of robotics dictate that we simply scale up the video world models to ridiculous sizes and let them drive the hardware as a mere afterthought.
Once the reasoning is solved, the control is just a single-layer projection away.
It definitely frames the scaling laws in a new light. That's all for this breakdown. Catch you on the next analysis here on AI Paper Slap.